In today's video lecture, we're going to introduce and derive the heat diffusion equation. This is also referred to as the heat equation or the heat conduction equation. I typically like to call it just the heat equation, just for brevity, and that's a pretty ubiquitous way of calling it. So what is the heat diffusion equation? So this is a pretty fundamental equation, especially for conduction problems. We're going to use this over and over again. We're introducing it in Chapter 2, but we'll also use it in Chapters 3, 4, and 5 quite extensively. So we're going to look at all different types of assumptions that you can make to simplify the heat diffusion equation under different geometries and different circumstances, and then solve each of those accordingly. So the heat diffusion equation is a differential energy balance. You've heard me really emphasize the importance of energy balances and energy accounting. Well, this is where it's going to be critically important to be able to think through what this equation means and where it comes from. We're going to use this equation to solve for a temperature distribution or a temperature profile in a solid. So just like before, in previous video lectures, we've used an energy balance to solve for an unknown temperature. Well, in this case, we're going to use this differential energy balance to solve for a continuous temperature profiles. So this equation is derived by taking a big solid and breaking it up into a bunch of small chunks. Each chunk of material, also known as a node, is going to be represented by a control volume. So remember, you can do an energy balance on any control volume. So we're going to do an energy balance on just a really very small chunk of material that's embedded within a bigger solid. So this is something that we are going to calculate the energy balance, then we're going to shrink that node down. And so we'll see that this ordinary differential equation that we derive will become a partial differential equation, which we'll be able to solve for a temperature profile. So it does become a PDE, and temperature is going to vary with time and with 3 spatial dimensions, and those would vary depending on our coordinate system. It's also going to have a generation term, and then once we've derived this equation, we'll be able to use it repeatedly over and over. So it's really important to remember that the heat diffusion equation, or the heat equation, comes from an energy balance. So we're going to derive it here this once, and then you'll be able to use it a bunch of different times, but just know that it's an energy balance that you're solving to find your temperature profile or temperature distribution. Okay, so the way to go about deriving this is so we first consider this big solid chunk of material. So we're going to take this big solid and we're going to break it up into even smaller little chunks or nodes, and we're going to consider that one of the nodes is going to be totally embedded within the solid. So if you think about, if we're trying to do an energy balance on something that is totally embedded, so let's say this is a big giant rock and we're doing an energy balance on a little tiny virtual cube that's right in the middle of that big giant rock. So how does energy get in and out of a solid like that? Which mode of heat transfer would that be? And hopefully, if you're keeping up with the lectures, you should know off the top of your head that this is going to be conduction. And if not, I'll just explain why not. I'll explain why it can't be the other modes of heat transfer. So if you recall, convection requires an interface between a solid and a fluid. Convection is heat transfer from a solid surface to a fluid that is adjacent to it. So in this case, because our control volume is totally embedded within a bigger solid, there's no surface for convection to happen. There's no fluid touching this guy. It's totally surrounded by the rest of the solid. Radiation also can't happen. Remember, radiation is going to be a surface-to-surface phenomenon with space in between those two surfaces. So in this case, there's no space in between. This solid is completely embedded. So conduction is the only mode of heat transfer that we'll need to consider here. But basically what we're going to do is we're going to take this small cube and consider that to be our control volume. And if we blow that up, it's going to look something like this. So rather than just doing a really simple algebraic energy balance, we're actually going to have energy coming in different directions. We're going to consider each face of this cube separately. So we could have energy coming in the left face and then leaving the right face, coming in the bottom and then leaving the top, coming in from where you're sitting into the screen and then leaving out back in the back of the screen. So we're going to do an energy balance that takes into account those different directions, but it's going to have an in and an out term in each direction. We're also going to consider an accumulation term, the energy storage, and a generation term. And I'm going to draw my own figure because I like to do the derivation a little bit differently. So let's look at our little cube that's embedded within a bigger cube. Okay, let's say that on one side it is going to be delta x wide, and let's say it's going to be delta z tall, and let's say it's going to be delta y deep. So if we do an energy balance on this guy, we need to consider that volume. So let's look at how our energy balance looks. And again, this might seem complicated by the time we're done with it, but really we're just breaking this thing down into simple terms. We're just being energy accountants here. We just want to be very careful with how we are describing energy coming in and out and keep track of each of these terms very carefully. So our energy balance, we start with accumulation. Then we're also going to have in, out, and potentially generation. So we're going to consider each of these terms. So our accumulation term, we would think about this in terms of, so we'd have rho, the density of our solid chunk, Cp, which is the heat capacity of our solid chunk. We're going to have the change in temperature of our chunk with time. So this chunk, it can be any dimensions we want. We could think of it being really, really small. So if we think of it being really, really small, it's a pretty great assumption to assume that the temperature throughout is totally uniform. And actually what we're going to do is we're going to consider it to be infinitesimally small. So this is a perfect assumption to consider that temperature is uniform in our little cube. Okay, so this is our accumulation term, part of it. We also need to multiply by the volume. So what is the volume of a cube or a rectangle? That's going to be delta x times delta y times delta z. Okay, so now how is energy getting into our cube? So we're actually going to break this up and consider it in 3 different dimensions. So we'll have x going from left to right, z going up and down, and then y going in and out of the board. So in our coordinate system, this left-hand side of our cube would be x. So because we have a cube right now, we're thinking of it having an actual finite dimension. So the right-hand side would be measured to be at a distance x plus delta x. So what I want to do is I want to take our in and out terms and consider them in these 3 different dimensions, x, y, and z. Okay, so how is energy getting in to our cube? It's in the x direction. We have energy coming in as a flux. This would be the qx of our system. So energy is going to come in according to this conductive heat flux, Q double prime X. To be consistent, I want to use rate of energy terms here. So we want each term to have units of watts. So remember, flux has units of watts per meter squared. So we want to take this heat flux in the X direction and multiply it by the appropriate cross-sectional area to heat transfer. So if you can see, maybe I'll just get a laser pointer. So our flux is going to encounter a certain cross-sectional area as it goes across from left to right. So that cross-sectional area, as you can see, is going to be delta y times delta z. Whoops, got to get my pen again. Okay, similarly, if we have heat, let's look at the z term, it's a little bit easier. So z is going up and down. So if we have flux coming in from the bottom, what's the cross-sectional area that that flux is going to be encountering? So we have our qz, it's going to be encountering a cross-sectional area of delta x times delta y. Similarly, for flux going into the board and then out the back, we've got our y flux, and that's going to be multiplied by delta x times delta z. So now how is energy getting out? Again, we're just sort of arbitrarily assuming that heat is flowing from left to right in the x direction, then from bottom to top in the z direction. So energy is going to be leaving from this side at potentially a different rate. So leaving, we would evaluate our flux in the x direction. Instead of measured at x, we're going to measure it at x plus delta x. But it is going to have the same cross-sectional area that it encounters of delta y and delta z. Similarly for the z here, energy is going to be leaving the top at a rate of qz plus delta z, q double prime. So we have q double prime z at z plus delta z. So this just means we're evaluating our flux at that particular coordinate, z plus delta z. So the cross-sectional area here is delta x times delta y, and similarly our y term is y plus delta y, and it's going to be multiplied by delta x and delta z. Okay, so that's how we're dealing with the in and out terms. Ultimately, we're going to add or subtract all of these terms. So we're going to treat each of these mathematically separately, but it just helps to organize things a little bit better by thinking about them in terms of the terms coming out according to their direction. Okay, we also definitely want to consider generation here. So I'm going to use this generation term of q dot. And if you recall from previous lectures, q dot is a volumetric generation term, which would have units of watts per meter cubed. So we want to take this volumetric generation term and multiply it by the actual volume. So it's the same volume that we used here of delta x, delta y, and delta z. So you'll notice I've been really emphasizing being able to, in previous lectures that is, I've been emphasizing being able to express the rates in terms of the rate equation. And you notice I haven't actually used any rate equations yet. We're just considering, we know these are going to be by conduction, but we're not thinking about that just yet. And I'm doing this just to make our lives a little bit simpler. So this next step, we've laid out all the terms of our energy balance. So the next step is going to be to just go ahead and compile this. So we have accumulation equals in minus out plus generation. And on the next slide, we'll go ahead and compile this. So we have rho Cp dt times delta x, delta y, and delta z is equal to, and I'm going to lump terms here according to the spatial coordinate. So we've got our flux as measured at x, subtract our flux as measured at x plus delta x. So remember, in minus out, but then we also have those terms being multiplied by the appropriate cross-sectional area of delta y, delta z. Okay, similarly for our y terms, we have qy minus q double prime y plus delta y. Multiply that by the cross-sectional area of delta x times delta z. And then we've got our z term, so q double prime z minus q double prime measured at z plus delta z. And then we multiply this by delta x, delta y. And finally, we have our generation term of q dot times delta x, delta y, and delta z. So far this is just an energy balance, and it's actually still fairly simple. And we could actually go through and check the units on all of this. And so here we'd have flux in watts per meter squared multiplied by two different distances, so that would give us meters squared, so overall we'd have watts. Here we have watts per meter cubed multiplied by a volume, so we'd get watts there too. And it's a little more involved for the accumulation term, but not so bad, but that ends up being in watts as well. All right, so now our next step is we thought about this little square in terms of, this little cube, sorry, in terms of finite dimensions, delta x, delta y, and delta z. So one thing we want to do is we want to divide by the volume, divide both sides by the volume. So let's go ahead and do that as an intermediate step. So we get volume cancels out. Here we get rho times Cp times the partial of temperature with respect to time is equal to Qx double prime minus Qx plus delta x, and that is also double prime. So one thing that's happened here is because we divided this by volume, the delta y and the delta z cancel out, but we're left with this delta x hanging out on the bottom. Similarly, for y and z, we end up with a delta y term and a delta z term. And then we can't forget our generation term, which I'm going to squeeze in there, which is much easier now that the volume has been totally divided out of it. Okay, so this is the form that we have this equation in currently. So now we could actually, so we can use the definition of a derivative. So we could say that Q as measured at x plus delta x minus Q as measured at x divided by delta x is actually equal to, when we shrink x down, so if we took the limit as delta x, delta y, and delta z all go to 0, we end up with these just being derivative terms, and actually the inverse of the derivative. So we have dqx with respect to x. So the step I skipped was taking the limit as delta x, delta y, and delta z all go to 0. So as we do that, we just shrink our cube down to be infinitesimally small, and then we end up with this nice definition here. So if we substitute this in, notice that this is flipped. So we're going to have to pick up a negative sign here. So we have rho times Cp times dt is equal to minus the change in flux in the x direction with respect to x. So we just used that definition of a derivative, but we had to flip the terms because here we have qx minus qx plus delta x, and here we have those terms flipped. So we have minus dqy double prime times the partial y minus the partial derivative of the z flux with respect to z. And we still just have our generation term, just haven't had to do much with it. Okay, so we're almost there. So we've kept all of our terms in terms of just these generic flux terms. So now we can invoke Fourier's law. So now we would apply Fourier's law, which tells us that Q in the x direction would be equal to minus K times the change in temperature with respect to x. So we can actually go into each of these terms and make this substitution here. So we're going to go ahead and do that now. So we're going to just substitute in, wherever there's this qx double prime, we're going to substitute in this minus k dt dx. And so as we do that, what we get is rho Cp times the partial of temperature with respect to time is equal to the derivative with respect to x of this quantity, which is going to be k times dt dx. So where did that come from? So again, we just substituted in. We substituted this part into here. And notice, I skipped this step, but we have a minus sign here, and we have a minus sign here. So because a minus is just a constant, it's like multiplying by minus 1, we can just pull that out, and this actually becomes a positive term. Similarly for y and z, so there's the y, and here's the z, and then still our q dot is just there by itself. So this is the final form of the heat equation in Cartesian coordinates. So it looks, again, it looks quite nasty, and those partial derivatives look intimidating, but again, trust me, stick with me for future lessons, and we're going to take this guy and break it down and make it much simpler. So, but I do want you to remember, at least internalize this part. This all came from doing an energy balance on this infinitesimally small, on this control volume, and then we shrunk it down to be infinitesimally small. We took the limit as delta x, delta y, and delta z all approached 0. And through a bunch of math and derivation, we end up with this guy, which is known as the heat diffusion equation or the heat equation. So this will start to make more sense. I know it's, I like to do this derivation first because I really want you to understand that we're going to use this equation to solve for temperature profiles, but just like in solving those really simplistic energy balances to solve for a temperature, well, we can solve this more complex energy balance, which covers how heat changes with respect to space and time. And we can use this to just extract a ton of information about how temperature changes within a solid. So here is our heat diffusion equation in much nicer typeset form. So that is just exactly what we derived. So these terms that have the partial of temperature with respect to x, those represent the net transfer of thermal energy into the control volume, so in and out. And we started just with this simple energy balance, and then we just did some math. The q dot is obviously our thermal energy generation term, and then on the right-hand side, this is our accumulation term. This is basically how much energy is being stored in our system. And I have emphasized that we try to do our energy balances in terms of rate, so they could be expressed in terms of watts. But if you remember the step where we divided everything through by the volume, the units, so if you looked at each individual term here, you would see that they each have units of watts per cubic meter. And we certainly, that's what our generation term always has. And that's what our accumulation term always has. So it's still the same thing, it's just this is an energy balance per unit volume because we shrunk down our control volume to be infinitesimally small. So I'm showing this picture here because I want you to see just how powerful. This is the same picture I showed in a previous slideshow. This simple equation, so if we apply this and solve this over an entire large complex solid, this would give us temperature as a function of x, y, z, and also time. So basically, by solving this equation with the appropriate initial conditions and boundary conditions, you would basically get a video, a three-dimensional video for how temperature changes in a solid over time. So you could get something certainly as complex as this. Something like this is from a numerical simulation. So we'll cover numeric ways to solve the heat diffusion equation in this course, but there are also some analytic ways of solving it, when there are special simplifying circumstances.